So am I speaking loud enough? Can all of you hear me? Yeah. So the other way around, if you actually have a question, please raise your hand, because I cannot hear from my left side, so I have no localization. So if you say, I will like, where's the sound coming from? So just raise your hand, and then I can answer. And if you have questions anywhere, feel free to stop me, okay? So thanks for inviting me over. I want to talk about some of the work that we are doing with City of Nashville and City of Chattanooga. Primarily, I started the work with City of Nashville, and if a lot of you don't know Nashville, Nashville is a music city. And these days, Nashville is actually most famous for paddle taverns. I was actually telling others. So this is a very special transportation infrastructure that is driven by drunk people on bars, and the only driver is not drunk who's doing the steering wheel, right?
No Amtrak station.
Sorry?
No Amtrak station.
No. So in this particular case, and the other problem is, apart from all these funny transportation problems or funny transportation mediums, Nashville is also actually have seen in last 5 years a big sudden boom in number of people moving in. So as of last count, there are actually 100 to 120 people per day that is actually going into Nashville, right? And this is really driven a lot by the political structure of Nashville, the taxation, and actually a lot of companies that are coming in. So like Amazon, Google, Facebook, and really that creates a massive problem for the city infrastructure. And that's where we are actually working together with them to try to see what we can do. So in short, if you actually want to know a lot more about my lab, you can actually visit the site. What we really do is I work with the smart cities, and we treat cities as a cyber-physical system. So effectively, we look at the whole ecosystem of collecting the data, analyzing the data, designing interface, presenting the data back. It will actuate the humans and bring the results back, right? So that's why it's a feedback loop, and this is a classical cyber-physical system. When you design these systems at really large scales, you will see that there is a problem that you always ignore that shows up. How do you move the data within the time? And how do you move this massive data across this region? That's where I actually work a lot on middleware design. So by middleware, I mean that software infrastructure that's necessary for moving the data and making sure all applications can communicate with each other. Now, finally, after you do all of this, one of the first things is this data is never constant. The data rates change, right? The application criticality changes. You have the computation infrastructure is same, it's constant. So how do you manage which application should be running, which application should not be running? What do you do when something fails? So that's where I do a lot of work on performance and failure management. Today, mostly I'm going to talk to you about the first part, which is about the smart cities and what we do. And very specifically, I'm going to actually focus on my work with transit authorities and my work with the fire department. As I said earlier, right, so this is a chart that we actually created with the help of our metropolitan planning organization. You can see the chart on the left is a chart from 2010 about daily congestion levels, okay? See the chart projected into 2040. And I am ready to say that this is actually not accurate anymore. It will be far worse than this, okay? So that really becomes a big critical point. So personally, what I have felt, I live around 20 minutes away, 20 minutes of 5 years. Today, in the evening, when I go back to my home, it can take anywhere from 40 to 60 minutes, right? And this is all about the highway congestion. So what can really be doing, right? What can we do? The traffic congestion is increasing. Now, one of the big things is you cannot just keep on adding again and again to the roadways to try to increase the infrastructure, because there's only two ways to solve this problem. Either you create more roads so that those single vehicle occupancy trips that are moving, they will go on those new roads. So effectively, you have just increased the capacity of your infrastructure. Or the only other way is put people together into single vehicle or a large vehicle. A classic case is put people into transit vehicles. It will be surprising to you when we go down to the south around Nashville and other places, people don't use transit a lot. Most people actually prefer driving their own vehicle. And there is a reason for it. First, the transit accessibility is not very good. So there is a lot of places, if you have to go, you will have to walk a lot before you can get to the transit bus stop. In some places, the frequency is very low. And in some places, there is no spatial bus lanes, right? So what happens is that traffic congestion that I was showing you affects the bus itself. So effectively, you can plan any schedule, and that schedule will go haywire because the buses will continuously run late, right? And that affects the people who are trying to take the bus. So really the critical thing that happens to you is you have to actually improve how people get information about this transit vehicle. So specifically, and can you tell with this information that the bus is going to run late? Can you really predict delays ahead before they happen? So one of the things we actually did around 2016, we started with a challenge, it was called Global City Steam Challenge, and there was some NSF funding, and we created a very, very simple app. And this app was very similar to in Seattle, this was called One Bus Away. So the idea was that we will actually directly reach the commuters who could have taken transit, who are not taking transit. So for example, all the students of Vanderbilt University, we tried to give them the data, right? We tried to show them, okay, what is the real-time view, how the buses are running late. We could actually tap into their calendars. So we would tell you before you actually wanted to go on a trip that there are few options for you to go to your destination, to your meeting, and how long ago you actually have to get to the bus stop and which bus stop should you go to, right? And also we started doing some social experiments where we would actually show them at least the information of what is the benefit of they taking the bus or not taking the bus. But one of the most fundamental part in all of this was really trying to actually handle the delays that the bus is encumbering. And can we actually help tell people before the delays happen that how much delay is going to happen? And when you start actually looking at the delay prediction as a problem, you will find there are multiple timescales in this. So one of the very basic timescales is real time. So real time is effectively if a bus has been running a few minutes late, you project in the future how late it will be running. The other thing is actually very long term. So long term is, can you actually tell typically in one particular seasons the bus runs later versus compared to the other seasons? What happens if there is a lot of snowfall? If there is a lot of snowfall in Nashville, forget buses delay, buses won't work. In Nashville, 2 inches of snow means city shuts down, okay? And the other thing is, if you actually have a game, for example, sometimes in downtown around in Nashville, there are hockey games, there are football games, there are events. When these events are happening, do you know how late the bus is going to be? So those are the different infrastructures, or those are the different things that we can build, right? Now, one of the things that we can do, specifically for the real-time prediction, we can train based upon the past performance of the buses, how well it correlates with the future performance of the vehicles on the same route segment. Now, there is an interesting thing that's happened. In Nashville, the bus service is very sparse. So what does that mean? There are not very frequent buses that go on all the possible routes. However, there are some routes which actually intersect with other routes. So what you can do is you can do an analysis and actually identify what are the common segments through which the bus goes. So now suddenly you actually have lots more data because you will have segment by segment data. And then on that you can actually train neural networks. So one thing that we do is something called multitask neural networks. Multitask neural networks are those that can actually learn from multiple areas, input sources, and then actually can predict final outputs. And we, of course, use it with Kalman filters to smooth things out. So this is an example of a real-time delay. And as the bus moves closer and closer to the time where it is actually supposed to be in the schedule, and closer and closer it gets to the stop, the confidence interval improves. So that is the information we can give to the people, actually. Now, of course, this is just a real-time bus, right? So question also comes, what can you do with the long-term delay? Now, one of the things that we do is actually collect all the data from all the buses. That includes their AVL position, the stop times, the dwell time, and we collect this continuously every day in real time. Simultaneously, we also collect the traffic speed, average traffic speed of vehicles through the traffic probe data on each road segment, right? So now you can actually create a model that finds out which parameters are more important to the bus delay. So what is the importance factor? You can also see on the right, for example, you can also find which days of the week, around which hours of the day, the average congestion is the heaviest. And in this case, the congestion is really defined as the difference between the average speed seen during that time segment, normalized with the difference to the free flow speed, right? So then you can actually clearly create 3 separate models, one for heavy congestion days, one for lower congestion, and then try to fit in weather along with that. So on the left is actually a chart that we drew based upon the real delays and actually what we predicted, right? So reals are all the blues, and effectively the rough prediction was a regression equation, and this is only as an intercept on some simple chart, okay? So the idea really is that you can create these kind of models, and these are different decision models. And we have to, in this particular case, we use random forests, for example, to fit it well, right? So you get different decision trees. Now, of course, what you can also do is not only look at very long term ahead, but you can look at just effect of certain events in the city. So one of the events that actually happens, by the way, not football game in the city that really affects things a lot, is CMA. Anybody knows what CMA is? Country Music Awards. Yeah. So when there is Country Music Awards, and Nashville is the country music capital of the world, right? When there's Country Music Awards, everything shuts down in the city around the downtown, right? So then there are detours, then there are delays, right? So one question that came to us, and we started looking into what, okay, can we actually capture these patterns and find out how these patterns changes, specifically if we plot the bus delay on the route network. So in this case, typically the delay is what is the typical time of operation minus the actual average time of operation during that particular time, and normalize it with the total length of the trip. So you can actually get 5%, 25%, how much is the congestion. And this is really congestion in terms of the bus itself. We can also actually find congestion or delays per stop. It's hard to read the stop variables, but these are each stops. You can find out how much is the delay, right? So now the question becomes is, can you actually take this and learn from this? So you have 2 information. One information is you have congestion maps, which are delay maps, right? Second information you have is time window. So this was, for example, this is 3 to 2 hours before the event. And you collect this for a lot of events, basically, that happen of the same kind. So in this case, football games, right? Because CMA actually we didn't really have the data for, so we did this with football games. And then you can say, okay, can we learn from it? And if you think about it, what you are trying to do is learn from various sets of images and create an average image outside. And that is the prediction of basically the delay, what will happen if there's a particular event. So one thing, yeah.
So we tried to do something like this once, and the events vary so dramatically depending on who's playing. Like, so, you know, sometimes they're big games, sometimes they're little games. And also what we found was that because people knew the game was happening, a lot of people avoided the area, and so you didn't see the bump that you thought you might see.
Yeah.
Did you find the same thing?
No, we didn't actually. So in this particular case, so most of the people in Nashville already know Titans are going to lose.
So they're just hardcore fans and go.
Yes,
anyway.
so mostly hardcore fans go, but that's a problem, correctly, but we didn't see that problem here. Sorry. Yeah.
What a place like Salt Lake City, they store buses or streetcars at the end of the route, both ends of the route, so they can just, depending upon, so they just don't allow the vehicles by demand.
Yeah. No, in this case, specifically the city was not necessarily, so Nashville is a city with constrained budget, so they were not able to add new vehicles. They ran the same frequencies, and they actually saw the delay. So this was one of the reasons we did this analysis, because we wanted to create a tool that we can give to the city, that when you do these kind of events, what happens? Can you actually see the progression of the change? And that's why we actually did this analysis primarily.
And
Yes.
what did they do to, in response to
Nothing.
Nothing.
Yeah, they said when we have money, we will actually add service. And they don't have money. Actually, right now, 2 months ago, they actually kept 10% of the service.
Well,
So-
people think they're going to solve the problem with the freeway. You have money, the price of the freeway.
There is a lot of problems in Nashville. So one of the things is the political climate is such that there is a new mayor that came in, and that changed completely the focus, right? So right now, Nashville's focus is Vision Zero. They want to avoid all the pedestrian fatalities. So that's what they're working on. Yeah. So, of course, one thing which we did is, and this was quite an interesting thing, that you take all the data and you transcode it as images. And you cut the images in just the right size so they look very symmetrical. Okay? And then you pass these images, and there is some technique that I'll just talk about through which we can generate new images because you need more, a lot of data. Then you can train a class of convolutional neural networks, and then you can predict effectively. It will learn that this is the output, and it will actually give that output of the image, then what will be the delay. So specifically, of course, what we had to do was, one of the things is when we look at the football games, there are not that many. So one of the things we had to do was generate more data. So we had this 2 to 3 hours, so we started averaging them, combining them together, and generating new data. This is very similar to how you will do any kind of genetic optimization, where you take 2 chromosomes and then you will actually divide them by half. And of course, we tried to compare what the result is, and we trained a random forest, and our accuracy was actually surprisingly pretty high. And this is the reason I don't think there was that much of a shift in the football game. Now, I cannot guarantee this will work for any other event, right? But one of the bottom line was, the observation was, by taking the images and using them to encode the data, we were able to actually encode both the graph, the shape, right, the correlation, spatial correlation, and then we got the temporal correlation. So something that we should actually take a look in the future is how can you combine this with, for example, graph recurrent neural networks, and then try this. This was, we did like 3 years ago, and at that time it was just a regular convolutional neural network that we designed to pass this. Now, when you pass a lot of the time of the day and other kind of information, you can use something called one-hot encoding. And that's what we did. And ideally, one-hot encoding, what it does is it allows you to encode in different part of images, a single image, some labels and information. So effectively, the time of day would become, it will start with black, and then if there's weather, it will become red, and that becomes a one-hot encoded vector. And you can send it as a second input to the neural network to learn, right? Now, of course, in this case, the accuracy was good, but I cannot guarantee the accuracy will be good in almost other places. Now, one thing that we did was we actually started working with the city, and we showed them what can you do to optimize your schedule. So because we have the delay model, we know how delays changes in various seasons. So we were able to actually update them a different route schedule per trip schedule per season. This they are implementing. So this was actually one of the big wins, trying to convince them that, hey, you should try to update your schedule, because the schedule that you are generating right now manually is not good. So, and you can see the effect from original to an optimal effect. Now this is something we can never tackle. This is called I-24 highway in Nashville. And this I-24 highway is very congested and very unreliable. So we couldn't tackle that. There was too much variation. But everything else, we could actually do it.
So basically you just adjusted the schedule to account for the congestion.
Correct. But
so level of service is wonderful now.
right. But one of the big things is actually to assign these, it becomes an integer programming problem, trying to make sure that the same bus is actually available for the next trip, because they have trip blocks. And this integer programming problem for a large number of buses in the whole city is actually intractable. It will become really, really hard to solve. So that's why we have to use heuristics. So common heuristics that we use is genetic optimization. We try to solve for small case with integer programming so we can see the balance, the gap, but for a full city, you really cannot do this on integer programming. It becomes very, very hard. So does that answer your question? Yeah. So of course, the obvious thing that next happens is that, okay, we did all of this thing. What can we do to actually try to improve the operations of the city? So of course, scheduling was one part, but the other part was we actually also started working with them, and this I heard today also that you guys are also working with flex stops. So we started actually suggesting them where can you actually put flex stops, and flex stops are those things where the bus can sometimes go through those stops and sometimes the bus will not go through those stops. And if a flex stop is there, flex stop will be on a part of a route at a particular time of the day, and for the other time of the day the flex route will not be there. Okay, so on certain fixed route services, for example for Route 7, we can actually say this is where you actually need certain flex stops. So the problem really becomes is, given a particular travel demand, you understand the travel demand, the OD pairs, can you actually identify where the flex stops is, and can you design a route through those flex stops? Now the biggest problem in this is, of course, there is some uncertainty in the travel demand estimation itself, and there is some uncertainty into travel behavior itself. So this is why when you do this, this actually becomes a class of stochastic optimization. So you have to frame this problem. If you try to frame this problem just as an integer optimization problem, it will require deterministic answers. So we frame this as stochastic optimization problem, but we start with something basic. So one of the first things is, from all the demand, we actually want to do flex stops. Where should the stops be? And here you can use various different kind of clustering algorithms. So one of the clustering algorithms that works very well is DB scan. You can use hierarchical DB scan. K-means is hard because K-means is typically a clustering algorithm that a lot of people like, they want to apply, but K-means works with, you should know how many cluster centers you're looking for. So this is why you actually go for DB scan or something like that. Now of course, after you do this, you actually have to actually set up an optimization function. So one of the first optimization function, and this could be different for different cities, this could be different for different transit services, but it will become a multi-objective optimization. So one of the optimization is how many people you want to serve and how much delay. So if you change the flex route, so what that flex route means is, bus is part of a fixed route and then it will move around and go to another stop to pick people and then come back to the fixed stop, for example. In that case, there will be delay that will be introduced. And you have to balance that particular delay. Now, this particular thing will also actually be subject to certain constraints. So for example, you need to actually put that the total sum of delays is greater than the slack time. So if you keep adding delays on the routes, this can never go more than slack time, because if it does, then effectively you will start later on the particular trip, right? Now because this is probabilistic, you will actually convert this into a probability form and you put some threshold on top of it. Now also you can actually do, for example, the time of stops. Stops of the come before, its time cannot be larger or greater than the time of the stop next. And you can also come the probability that departure time of every stop is greater than the scheduled time, right? Because effectively, if the scheduled time was certain time on one of the stops where you are starting, the bus should always leave after that. It shouldn't leave before that. So these are actually classes of constraints that you start adding, right? And then of course, when you solve this, right, again, this is a class of problem. It is hard to solve with integer programming, so you can again use genetic optimizations. So one of the things that is actually under consideration right now with the city, and we were just using the Route 7 as a study to try different flex stops. So these are 3 different times that we suggested to them between 9 to 10 itself. And this is a time where different people go to offices at different times. And this is something they are ready to evaluate. They are going to try it. And this is where we are actually working with them to improve these scheduling capacities, trying to reschedule. So I think this is one of the way we can actually improve the transit operations if we try to mix micro-transit kind of behavior with the fixed transit kind of behavior. So you try to mix the two, okay? And specifically with the city, where these are really, really important, they don't have too much leeway, they don't have too many resources, they can do that. Now, of course, one of the things in this case also comes is, a lot of times you can route and schedule based on travel demand or demand time. But we actually started working on a DOE project where we started looking at, okay, what if it is not the travel time, but what if it is about the total energy of operation? And why is that energy of operation important? Because it is directly related to the cost of operation. So one of the things that we saw, we actually worked with Chattanooga and we put in their vehicles various OBD2 sensors, okay? And these sensors were, for example, routed, brake, arrival times, electric buses, state of charge, speed, voltage, current, power, levels, and you're getting this at 1 hertz. As the bus is moving, you're getting these readings continuously, right? So now you can actually integrate these readings, and you can plot them over the route. And you can say, okay, typically compared to all of the other times, and if you normalize the energy consumption by the length of the route, how much is the variation? So this is a figure from Chattanooga where we were doing projects. What you can see is that around this is for electric buses, these routes in between 3 p.m. to 6 p.m. are very heavy consumption on electric bus. Versus on these routes, this is lower consumption. And we compare this against the diesel buses as well. So now what you can do is the same kind of formulation that we saw in the flex top case. You can convert them into a formula that actually tries to lower the overall energy consumption. Okay? Now, what you have to do first for that is actually you really have to create a good model that can actually learn from the past, those times, and can predict if you put a particular bus on a particular route, what will be the total energy consumption. So this requires a lot of steps. So for example, one of the things is the map data that we get, the GPS, it's very noisy. From each bus we get the location, which exact route segment it is. This requires a lot of effort trying to do the map fitting. It's not easy. But once you do that, you can actually train, for example, any kind of decision framework. You can use regression, you can use random forests, you can use neural networks, and you can actually say, okay, on this time of the day, at this particular traffic, what was the energy consumption of that route? So that's what we did. Yes?
So don't you know where the bus is going because it has a fixed route?
Yes.
Okay, so you didn't really need to map. You kind of knew where they were.
But we didn't know exact, so we were doing it as it travels, route segment by route segment. So we didn't know whether it is in that segment or not. So that's where it basically bounces off. And this is one of the things that we do. We have a factor to correct the GPS signal. We estimate that it is supposed to be in that segment with that. So then we will move that GPS point to that segment. That's what our correction is actually. Now, of course, you can actually start planning this. Again, you can do this with integer programming, right? You can do linear relaxation of the integer programming, right? And then you can use various different kind of heuristics. And you can also use genetic optimization. So this is one of the things that we did. And when you are trying to assign the heuristics, could be done 2 ways. One, take all the trips that you have to run and assign bus per trip. And keep doing it and keep solving it 1 trip at a time. And you can say, I'm going to try to do with the longest trip first and then go back. The other way you can do this assignment is you pick a bus and you try to find the cheapest route for that bus and assign to the route, because there's 2 problems, right? This is a matching problem. You can either start from the bus or you can start from the route, which is in this case is trip. And you have to try to match the 2. So those were our 2 heuristics basically, whether we do the trips first or whether we do the bus first, right? And overall, when we actually run this, we got around 10% of reduction. And what we found was that actually the answer between the heuristic algorithms and genetic optimizations or even the linear program are not that far away. So effectively, we can directly use the heuristic algorithm itself. These are actually just results right now. We have not validated it in actual buses, but this is planned for the next part of this project. It will be done later this year. With that, if it really does work, then we believe, actually, according to the study, that we can around do 10% reduction of energy consumption for the whole fleet. And this is effectively a mixed fleet. That saves a lot of money for them, right? Now, so really, when you look at transit, you have to attack this from both sides. One, you have to try to make the operation efficient. So try to actually add new stops, being a little bit more flexible. Try to reduce the cost of operation, so you can do energy optimization. And from the other side, you really want to tell the passenger everything about the bus, whether it's coming late, whether it's not coming late, how late it will be, and all that becomes part of the solution. And that's what we are trying to do in Nashville as well as Chattanooga. Okay? So, are there any questions on this part? So, let me actually talk a little bit another interesting problem which is very, very similar. And again, this relates to congestion. So one of the fundamental problems that happens with the congestion is that emergency response also shows fluctuation. And why is that the case? If emergency response had a siren and it could go the fastest, why is this the case that actually it will show a variation? The problem is if the whole roads are clogged, you will actually get delayed further. The ambulance might reach faster to the location, but it will still have some delays, right? So we were asked to come up with a policy for them to actually improve the response time, the overall response time of all the incidents that are happening in the city of Nashville. So, and if you actually start thinking about it, on the left, these are all the accidents that are happening, and this is just in January 2018, right? That's one of the test data sets that we did. And we actually have accident data set from effectively last 3 years from Nashville and the surrounding counties. One of the first problems that actually happens is, if you see a lot of epicenter of the accidents is always in the downtown, right in the center, that's downtown. And if there is an accident and you send ambulances or fire trucks to that place, and if there's another accident that happens there, that same ambulance will be routed towards that. So what you will see is over time of the day, you will see an imbalance start to happen. A lot of places, ambulances are clustered. And some places when something like this happens right here, you actually have no ambulances there. And now suddenly the response time will actually increase. Okay? So the basic thing that happens here is you want to balance out the resources over the location of the city based upon what your anticipated demand is. And in this case, anticipated demand is not travel demand, but rather the accident rates in the city. So classically, this is what happens actually today. And in most cities, this happens. You have a problem, you call 911, they actually have a locator on all vehicles, they will find which one is the closest, go. If that's the closest, that will go, right? And with this, specifically this kind of imbalance actually happens. And this is what I call is a reactive approach to solving the problem. Now obviously, the opposite of reactive is proactive, right? So what do you mean, what do I mean when I say proactive? One of the things is you are not anticipating the demand at all. In the current model, you're not trying to anticipate what will happen later in the day at 4 p.m. or around 12 p.m. What is going to happen? The second thing you are not doing is all the resources are either typically, and by resources I mean the ambulances or the fire trucks, they are typically located in the station where they are supposed to be. And then they are dispatched either from the station or the previous side. So the key idea is, can we actually, and think about it this, can we move the ambulances and fire trucks and park them in certain parking lots if we know there are problems that are going to happen? Because this is a hotbed of activity, and then the response will actually decrease. And the next thing that you can do is when you are trying to send an ambulance to an accident case, you can actually ask yourself how serious the accident is, and do I need to send the nearest one, or I should actually send something else that is slightly farther away, right? So that's a little bit proactive approach. But of course, in order to do that, one of the first things that you have to do is you have to learn what is going to be the likelihood of an accident in a given region. Now, one of the things that you cannot do is actually, and this is what a lot of papers try to do, they try to predict whether there is an accident that is going to happen at a particular location at a particular time. The answer of that is 0. This is a Poisson distribution actually. What you can ask is, what the question that you should ask is, what is the probability that there will be more than 2 accidents or more than 4 accidents in a particular location in a particular interval? Or you can ask the reverse, which is an exponential question. What is the rate, inter-arrival time between 2 accidents on an average in a particular location of a city? That's the question that you should ask. Now, of course, that is the question we ask, and the question becomes is, can you learn what this rate is? And the way to do that is you have to first come up with a chart where some rates where there's a time of occurrence, and you have in the rows all the other features that could have affected the accident. So for example, the traffic congestion, the time of the day, what was the weather feature, right? Were there accidents in nearby or not? How many accidents were nearby? So you get all of these factors, and these becomes the features. And what we do is we divide the city of Nashville into these small grids. And initially we start with small grid, 1 square mile grids. And then we figure out what are the feature values in this case, features will become speed of the average speed in this grid. Or was there an accident nearby? And then we actually find which grids have various similarity because they become similar regions, right? So we start matching and meshing grids up. So effectively, after some time, what you will see is various models will appear where some grids are similar to each other and there are some other grids. So you get a clustering of grids. And on top of that, you can actually learn a very basic survival analysis model. Survival analysis is an exponential function, and this becomes a log linear model where you can say log of ti, which is the time of arrival, is some factor of some features plus some noise. And you're trying to learn this intercept. And if you actually have a lot of data, you can fit this very easily. And that's what we do. So typically what we do is we start with this model, collected all the data for different grid cells. We try to learn this equation, right? And then from that equation, what you can do is in order to try to actually estimate the best factor, you can use things like maximum likelihood. So how well is this model going to work, right? But this is where something actually happens. You can start with a model. This is the model that you learned from the past data. But however, in the city, things are changing. So for example, there could be new accidents, there could be new construction. These will not be part of your model at all. So effectively, you have to update your model. So this is what we call streaming survival analysis, where we start with an estimated model and we update this model, the features, as new data is coming in. So we calculate the inter-arrival time for the grids and then try to fit it in. And the way we do this is we actually use stochastic descent gradients, and we take our current coefficient and then we try to update it to a particular coefficient by computing the likelihood, and then with some discount factor we just move it up. And we do this continuously online. Okay, so effectively you get a model that is continuously updating. So we did actually an example. So this is a small short-term prediction. This was actually just the batch model. And we, in this case, to the model we introduced artificial accidents. These accidents were not real. We actually created, and we actually start putting in the model. We found that the streaming model actually can capture, in this area, these were more accidents, its heat map becomes strengthened. And this heat map is effectively the rate incident, okay? That's what it is learning. The other thing what we do is, in this kind of fitting, what you really want to do is you want to minimize the negative of log likelihood of how many times in this particular rate, what is likely. And the streaming model's log likelihood is much lower than the batch model's log likelihood. Now, of course, in order to really visualize how well it works, we actually calculated the prediction rate for the whole month of January, right? So you can also ask from now, what will be the total accidents, number of accidents that will happen in 31 days? Because this is a time model. We are learning it in minutes, so we can convert 31 days into minutes and say, okay, how many accidents will happen? Because again, it's an exponential distribution, right? Inter-arrival time. And you can, as you are learning, you can continuously change it as you get new data. So on the left, this is the predicted total rate incident from Nashville. On the right is actually the rate that we captured from the real data, right, for the whole of Nashville. This is the rate average across 31 days of January, right? And you can see it captures very well most of the area. There's some areas that it cannot capture. And the reason is our hypothesis, we actually have sparse data in those regions. We don't have too much data from that region because there is actually, we recently were doing an analysis and there's a lot of gap in the accident databases of Tennessee Department of Transportation. They store these data from police, but sometimes data is just wrong. They just don't have proper accidents. And we compare this to Waze, for example. There are a lot of accidents that are in Waze that are not in the police database at all. And there are some accidents in police database that are not in Waze, and that's okay. There is a mismatch. And I think that's what is happening specifically here. Now, of course, when this happens, right, so one of the questions that comes in, okay, we learned these rates. And we can learn these rates for different grids. So, for example, imagine that red is more likely, blue is less likely, right? The problem becomes who to send. In this particular case, which ambulance will respond? So blue is less likely, red is higher rate. And if there is an accident and you only have 2 ambulances, which ambulance will you send? Blue, right? Because it is less rate, right? So there's less likelihood of accident, you may suffer less. So if the cost is the response time, which includes the travel from the previous location to the new location, then the cost will be lower. Now what? Right? So if you actually have this large grid, and you have some certain yellows and blues mixed into the picture, now who goes? It's not clear anymore. It's not so straightforward, right? So you literally, this is almost like a set vertex problem. You actually have to do set maximization here. You have to find out how can you cover these accidents from two of the vehicles, right? Now, of course, you can also turn this into a slightly different problem, which is called the stationing problem. So not when the accident happened, before the accident happens, can we actually move our ambulances around so that we are always clustered near the heavy areas versus slightly away from the areas which are not very heavy, right? So this is the problem that we are working on. This is effectively called the dispatch problem and the stationing problem. Now, formally speaking, you have the current location of the incident, and if you're solving the dispatch problem, you just want to find the near optimal resource assignment for this. Now, one of the things that we do is in order to solve this problem, again, this is a complex problem, we use Monte Carlo planning. So for example, we have all the rates from all the grids, and we want to use the Monte Carlo method to solve a Markov decision process, which effectively maximizes the total reward that we will get. And in this case, the total reward is basically the inverse of response time. We don't want too high of a response time, okay? So effectively, you have the current state, any grid waiting for service. You have the vehicle states. Vehicle states is where the vehicles are, right? And you have some environment factors. Environmental factors help you decide what will be the travel time from my current location to the location where there are incidents, right? And then you can actually direct the responder to the next incident. So the way we do this is we actually use a cost function where the cost is cost at current state, right? And the cost of parent state. And in this case, the parent state will become clear. Parent state is my current state, which I hold all the grids where there are accidents, there are not accidents, and where the current ambulances is. And I can compute the total cost from that state. And then I can move to the next state by taking a particular action, okay? So in this case, how does this work? And this is effectively like a Monte Carlo state. So I have my current state, I have the vehicle states, I have the running cost, this is the total cost from the parent, and I have a pending accident, right? Now, of course, in this particular case, you start with some time and you ask yourself, what are the next actions that we can take? This is the classical Monte Carlo approach. So this is, for example, was used in Go. AlphaGo, when they were playing Go, you are basically searching through the steps. So imagine you actually have a lot of actions where any responder with response time less than some discount factor is considered a candidate solution to go to this incident, okay? Now, we solve one incident by one incident, and this is the reason you can do that is if you have a continuous time distribution model over all the incidents, you can assume each incident occurs instantaneously and separately from the other incidents. They don't really happen together, okay? So in this particular case, as soon as an incident happens, we can find any of the responders that can go to there, find out the cost. If it is a legal solution, we actually put it as one of the next states. So to simplify this, assume that you only have 3 states. So in this case, this whole game board with all the grids and all the vehicles will move to a new position. Then you can ask yourself another question, can I simulate more accidents? Okay, and the way we do it is we have all the rates. We can create Monte Carlo chains of accidents. And these different accidents will create more chains. And then you can keep going forward. You can keep the same answer. Every time something happens, a new accident happens, you say, okay, what is the next vehicle that I should send? And you will keep on doing this till some stochastic horizon, and this is typically called the boundary, because you don't want to keep exploring always in the future. Once that happens, right, what you can do is from this point onwards, just assume any heuristic action, because you don't want to fully explore the space again and again. So in Monte Carlo, for sometimes you actually explore all the states, and then you can just say, okay, I will just take the next fast action. So So you start doing rollout. Okay. So in this particular case, we can start rolling out, and we will keep going, and then finally, which is a hyperparameter that decides our depth of the tree, we can compute what is going to be the final cost. In this case, if there were incidents, what will be the total costs of vehicles going to the incidents? And as you can imagine, we will pick the one with the lowest cost, right? And you roll it back. You find which part led you to that, and that becomes a candidate solution. So this is, in some sense, this is very similar to receding horizon control, if you guys are familiar with. That's how this works. Now, what you also have is, because this is parametric, right? This is stochastic. So one tree is assuming an accident happens in a particular grid. But how did you know in the future an accident is going to happen in a particular grid? You have rates. If you have rates, what you can do is you can actually create multiple chains of accidents. By these chains, these are called Monte Carlo chains. So sample out a sequence of sequence of incidents through this stochastic distribution, and you will get many such chains, basically. Repeat that same tree that I showed you for these chains, and then average out the cost across these chains. Okay? So for example, in this particular case, you take this, you assume all the particular costs, and then you will say always B, which is the action of moving a particular resource B, in that particular case, that will become the solution for you. Okay? And if you keep on doing this again and again, you will actually know what is the real-time dispatch solution. Now, when you do this, there is a lot of things. One of the things is you actually need a very precise simulator. The simulator is required to actually tell you and keep track of this tree as it progresses, and what will be the travel time from the new position to the old position. And of course, stochastic horizon and discount factor. Discount factor is basically, how do I keep track of future rewards? And you have to include it back in the system. Now, of course, when we do this, what we found was average computation time is pretty low, but really the big impact only comes if you actually have enough sparsity in the ambulances. So this problem does not make sense for a city that have a lot of ambulances already, because this problem will not happen. So we started comparing at what point in time Nashville has a problem. So if there are only three vehicles, then a lot of them get impacted. And also, you can also find out how much time you will save, right? So on an average, in this particular case, we got 38 seconds, and 38 seconds is a lot for response time for a single incident. Because this really, if you are having a heart attack or if you have a problem, 38 seconds could actually mean the difference between life and death. Okay? So that's effectively the way we solve the Monte Carlo problem of emergency response. And remember, this only is working possible because we actually have the predicted rate of incidents, right? That's how we can do this. All right? So I will skip for the lack of time. There's some new work that we have done, which basically starts with the same kind of Monte Carlo planning, but it does in a decentralized manner. So what that means is we plan separately for each ambulance. Okay? And the reason you do that is because what if the communication has gone down, where all you have is an information of incidents? So as a multi-agent system, can I take my own decisions? And here we are asking the question, can each ambulance take its own decision? Okay? So we did the same thing, but when you do decentralized Monte Carlo, which is a very new thing, when you do decentralized Monte Carlo, you have to assume what the others are going to do. And if you try to actually solve strategically, and this is where the big problem comes, you try to apply strategy to all other individual ambulances, your state space will explode on you. It will just not possible. So you need some simple heuristic answer. So you can do two heuristic answers. One, if I'm evaluating for one agent, I say other people don't do anything. They are greedy. They're not going to move. This is called the greedy approach. The other is you can actually form queue-like approaches. So incidents are queues, servers, and ambulances have to respond, right? And you can find out with the queue waiting time what will be the waiting time of each incident, each response vehicle moving to a particular incident. And that's how you can actually form a decentralized Monte Carlo approach. And then the same old thing works, right? And in this case, we found something very, very interesting actually. Our response time can really be improved a lot if we actually know the strategy properly and we know the strategy of the other responders. Okay? So these kind of Monte Carlo methods work. And the best thing is, in this particular case, this Monte Carlo method actually doesn't even need communication. All it needs is to run on an ambulance. And it can actually solve how to respond to a particular accident. Okay? Do you guys have any questions about this part, the ambulance part? Okay, so now just changing things. One of the things that this is sort of the closing point that I want to say. We do a lot of these things, right? We build a lot of solutions. But one of the things that people are not necessarily looking for when they are building the solution is you have to understand the change. So for example, in the ambulance case, we understand the change of rate of accidents over a region. But you also have to understand faults. So what if your communication breaks down? What are you going to do? This really creates a different kind of complexity for the problem of this multi-agent setting. It becomes much, much harder. And to make matters worse, if you really, really think about it, we don't even know how the different components really interact at really large scale. So for example, if you're really interested in actually modeling faults in these systems, these applications, and you try to understand where the faults come from, this is such a big software stack followed by the physical stack that you have no understanding. It's complete spaghetti. So right now, most of the time it is best effort, just do it and sell it and it's fine. That's why most cities, when they use these tools, one of the things that happens is if it fails, they always have a backup. They will do something else. Okay? So this is really something, when you are building these classes of systems, you must think about how to solve these problems in a way that they can remain resilient even under faults. Okay? So thank you very much.